Hi, and welcome to this next video in our series on trigonometry, and we're going to be looking at trig equation identities, and we're now going to extend our knowledge a bit beyond GCSE. Some of the stuff you'll be familiar with, but some stuff, particularly the identities part of it, it will be the new bit for A level, and hopefully you'll start to get a sense of what we can actually do with trig and what a massive topic it is. GCSE merely brushes the surface. So what we're going to do is have a look at trig equations, use these things called trigonometric identities when solving them. We're going to have a look at trig equations that are quadratic in form, and then again keep looking at sine, cos, tan, and particular values of sine, cos, tan that lead to some exact values using surds, which you should be familiar with, and then finally look at doing some proof with trig identities. So quite a bit to get through. We're not going to all hit it all in one video. In this one we're going to just have a look at the equations. We'll save those two bottom ones for other videos, because like I said, there's a big chunk of stuff to get through here. So here we go. This is the stuff that you'll be familiar with, and what we're really making sure we understand is that when you solve a trig equation, for example, like the ones that are popping up on the screen now, there's often more than one value. And the key thing here is the fact that you should be aware that you only get one value when you type it into your calculator, so you need to figure out how to make sure you're getting all the values that you need. And the thing with this one is, like, so you'll notice that these first two are just for values between 0 and 360, but sometimes that changes, so we've got a different range for values there. So just making sure we're clear on exactly which values are relevant in our solutions and which ones are outside the range that's been stated. So, enough talk, here we go. First one, tan x equals 0.5. Fairly straightforward stuff. To get x, we've just got to do the inverse. So x is tan to the minus 1 of 0.5. And from the calculator, that gives a value of 26.6. And hopefully you understand from the tan curve, there it is, that essentially all those values, those kind of that S-shaped curve is just, each bit is just shifted 180 degrees. So all we've got to do is say, okay, well there's our 26.6, which is just the first one here, that's that one. And then all we're going to do is add on 180, and we're going to get our next solution. And so our other value is 206.6. All fairly straightforward. Now we've got an equation that's starting to look a little bit more complex, but all we've got to do is a simple bit of rearranging. So take the 2 over, divide by the 3, and you get sine x equals minus 2/3. And now inverse of that, so sine to the minus 1, and we get x is minus 41.8. So again, that's the value of the calculator, but if you look at it, you see, well, we need values that are between 0 and 360, and that value there, that minus 41.8, is not in the range that we want. So again, what we're going to have is have a think about, well, I personally prefer to use the curves. It might be that you're a cast person, in which case you use your cast and you'll know how to do that, but I like to kind of sketch the curves so I can see what's going on. It's personal preference. Both methods work absolutely fine. And we can see, okay, well, this line down here, that's our minus 2/3. So that one there, so the value on our axis there is the minus 41.8. We can see we've got two values, one there and one there. And clearly we know that if that distance from there to there is 41.8, and if we go to 180, the distance to our new value has got to be above it by 41.8. And this one here has got to be 360 minus 41.8. It's a bit clearer when I stick those lines in. There they are. And so what we've got is 221.8. So that one is the 180 plus 41.8. And then we've got this one here, so we've got to come back 41.8 degrees from 360. So there's our 318.2 sorted. So in that case, we got our principal value off our calculator, the minus. It wasn't in the range we wanted, so we had to adjust to pick out the values that are in the range that's being stated. Okay, on we go to part C. And this one, now we've got an equation here that involves sine and cos. Now, this is going to be the new stuff, because in order to figure out what's going on with this, we need to know a little bit more about how those two trig ratios are linked. And you'll have seen previously that that kind of, from looking at the sine curves, the curves of sine and cos, they are very much linked together. But we're going to have a look at the relationship between them in this context here. So what we've got is our right angle triangle. There's our angle in the corner. And we know for this triangle that sine theta is opposite over adjacent. So the opposite side I've called y. The hypotenuse I've called z, so that's y over z. And similarly for cos theta. Right, now what I'm going to do is just take sine and divide it by cos. So sine theta divided by cos theta, which I'm going to write out in terms of these things here. So that is y over z divided by x over z, and you should know that in order to division of a fraction, you've just got to flip it upside down and change it into a multiply. So let's do that. There we go. And hopefully straight away you'll notice that we've got a z on the top there. We've got a z on the bottom here. So those two things are going to cancel out. And so what it leaves us with is just y over x. And if we have a look back at our original triangle, y is the opposite side, x is the adjacent side. So hopefully now you've seen what's coming. There it is, opposite over adjacent, which we know to be tan. So what we're saying is that any time that you do sine of an angle divided by cosine of an angle, what you actually get is the same as the tan of the angle. And this is the first of a great many number of trig identities. You're going to meet a couple in year 1 with your maths, and then a whole bunch more in year 2. So we've got this link effectively between all three of the ratios. Sine over cos is tan. So let's go back to our equation now, which was this one up here, and see how we're going to use that and this piece of information down here to help us solve that equation. So here we go. We've got 5 sine x equals cos x. And if I just divide both sides of that equation by cos x, I've done sine x divided by cos x here, and then cos x divided by cos x on this side just gives me 1. And from what we said earlier, we know that sine divided by cos is tan, so that thing can be written as 5 tan x equals 1. Now we've got an equation that's just in terms of a single ratio, which is what we need, and so it's a simple enough job to do some solving. So here we go, 10x equals 1/5, x is 11.3. Now, on the previous two examples, we needed values from 0 to 360, but this question is asking for values between minus 180 and positive 180. So let's have a look at what's going on. There's our tan curve, there's our original value, and you'll notice if we have a look at up this way, yeah, there's no other values in between 0 and 180 that have a tan of 1/5. So what we're going to have to do is subtract 180, and that gives us this one here. So the other value we're interested in this case is 180, minus 180, technically plus 11.3. You can figure it out. That gives you the 168.7. Right, so there we go. Our first small step into a brave new world of trig. We've got this identity, sine over cos is tan. And we used it to solve an equation. On we go. So again, another couple of reasonably straightforward equations, but this time, okay, we've got extra issues to deal with in terms of here we've got sine 2 theta, and here we've got cos of theta plus 50. So those are the things we're going to be looking at. How do we deal with this kind of stuff? Right, here we go. So we've got 5 sine 2 theta plus 4 equals 0. Proceed as we did before, so move the 4 over, divide by 5, we've got minus 4/5. And at this point, we need to be very careful, because the note there says that we've got to do that 2 theta is inside the sine function. So before we reverse the 2, so don't even think about dividing by 2 there, what we've got to do to begin with is do the inverse of the sine function. So what we've got is 2 theta is sine to the minus 1 of minus 4/5. So that gives us the minus 53.1, and notice my equation is still saying 2 theta equals that. Looking at the range of values, we've got from 0 to 360. So there's my sine curve, there's the minus 53.1, those are the other two values that we need. So again, that's going to be 180 plus 53.1 is going to give me that one, and 360 minus 53.1 is going to give me that one. So there are my other two values, and we can ignore that one, it's outside the range. And then the last step would be to do a divide by 2, so theta is 116.6 and 153.4. Now, unfortunately, we're not quite done yet, because we've got another thing to consider, which is the fact that when we do that divide by 2, what we're going to find is that it's going to bring more angles into the range that we're considering. So what we need to do is look at other angles above 360. So if we think about kind of where would be the next time this blue line hits the sine curve if we extend it beyond 360. So the next one, essentially, where that's going to be 360 degrees above this one here. So we know that 593.1 is also a solution to our equation 2 sine theta equals minus 4/5. And the next one after that, which would be 360 above the 306.9, is 666.9. Now, those two are outside our range at the moment, so our range only goes to 360. But as I said, when we do the divide by 2, when we do this final step going from here, 2 theta equals that, theta will equal that divided by 2. And so we've got 296.6, again, this one halved, 333.3, and all of a sudden, instead of our standard 2 angles being in the range from 0 to 360, we've actually got 4. So for these kind of questions, you need to extend your initial response beyond the range that you're considering, and then see what happens when, let's say, when you do divide by 2, or if it was to divide by 3, even more angles would kind of drop into the range that you want. So there we go. We've got our essentially 4 solutions. Now, why is it we've got 4 solutions? Well, let's just have a look at the curve y equals sine 2x. I'm going to, for now, just ignore the kind of the 4 and the minus 5 bit and just concentrate on the kind of the double angle part of it. This is our curve from 0 to 360, and what you see is kind of there's our standard sine curve, but you'll notice that's happening all between 0 and 180, and then it's repeating again. So what we've got is the whole curve repeated twice between 0 and 360, which is why we're getting 1, 2, 3, 4 values. Now, why is the curve repeated twice? Well, if we think about what's happening, you should go back to your work on transformations, and you know that if we've got sine 2x to 2 inside the function, so it's a horizontal stretch, and the horizontal stretch, the weird ones, they don't go the right way. It's the one where you've got a scale factor of a half. So that whole curve for sine 2x is being kind of essentially shrunk inwards, and we're getting 4 possible values. So that's why it's happening. And let's say it's just something you've got to be a bit careful with when you're dealing with equations of the form that one we just looked at. Right, moving on. Last question we're going to do. We've got something similar where we've got essentially a simple little kind of calculation going on within our cosine function, and so we've got to sort that out. So again, proceed as normal. We can see move the 7 over, divide by the 8. Again, now we're going to do the inverse cos, and so we know we've got theta plus 50 is cos to the minus 1 of 7/8. So theta plus 50 is 29.0. There we go. There's our cos curve. It's the one that starts at the top and goes down towards 90 degrees. And we can see we've got 2 values, 29.0 and the other one, 331.0. So that's theta plus 50 equals those values. So now, obviously, what I'm going to have to do is move the 50 over, do subtract 50, and we have a problem, because our range of values was from 0 to 360, and all of a sudden, we've got a negative value, and that's happened because of the minusing 50. How do we deal with it? Okay, well, what we've got to do is think about what would be the next value. Again, if we're going to continue this curve beyond 360, where would be the next time my blue horizontal line would hit the curve? And clearly that's going to be 360 degrees above that one. So if we just put in our extra value, there it is, 389, and then we've got theta plus 50 is 389. So now I've got to do take off the 50, and lo and behold, that 389 take off 50 becomes 339. That's brought that back into the range we want, and so there are our 2 values that solve our equation.